Good morning, I'm Alex Thorogood from EcoDrive. Welcome and thank you for taking the time to consider my research into SINES, Switched Intelligent Grid Network Systems, an alternative approach to power quality. In this overview I will discuss the background and founding reasons for the research, identify problems for the current grid structure from an end-user perspective, and consider both problems and opportunities, and attempt to address the problems in a practical sense through experimentation focused on an alternative approach. In conclusion, establish a future direction for development and experimentation. Research considered the national grid on the eastern seaboard of Australia and domestic installation on the Sunshine Coast in Queensland. The cascading blackout in USA's Midwest in 2003 threw the nation into chaos, prompting questions of terrorism, sabotage and foul play. 50,000 people were left without power for up to 2 days. What became apparent is the dependence that modern society have on grid to supply usable, reliable energy. The effect of the blackouts were catastrophic. Transport systems shut down, communication systems failed, trading ceased, and worst of all, domestic crime escalated. The cause of the cascading play was nothing sinister but a failed alarm system to notify operators when power lines collided with unpruned foliage during a storm in Ohio. The event prompted a 3-year review in the US by the Department of Defense and the Federal Emergency Management Agency, producing a report titled Brittle Power. The finding of the report was that network grid systems are vulnerable. Nevertheless, interconnected infrastructures where centralised generation creates the platform for increased efficiency, lowering energy costs and lowering greenhouse emissions. The longest interconnected power grid network in the world exists on the eastern seaboard of Australia, stretching from Queensland in the north through New South Wales, Victoria to Tasmania in the south, and South Australia in the west. Some 5,000 kilometres between the furthest points of Port Douglas and Port Lincoln. Some 850,000 kilometres of power line interconnecting 16 distribution networks, of which 80% are in rural areas. The network for its size is lightly loaded, with operators such as Ergon in Queensland having as few as 85 customers per kilometre of power line. The national energy market is controlled by the Australian Energy Market Operator, and energy is purchased at 30-minute intervals on the spot market. What this has meant is that ageing power stations, which are typically less efficient, are becoming uncompetitive. Since the commencement of the national energy market in 1998, as many as 7 power stations are no longer operating. Pictured is the Playfoot A and Playfoot B power stations and the Great Northern Power Station in Port Augusta. Both Playfoot A and B have now been shut down. Despite the number of closures of power stations, there still remains an oversupply on the network, with some stations operating at as low as 30% capacity, and there are no plans to add power stations in the foreseeable future. Ideally, power stations are best located near the greatest load. However, this is not always possible. For example, Queensland's greatest load is located at Gladstone, with Queensland's largest power station at the Gladstone Power Station, generating 1,600 megawatts from 6 coal-fired boilers. Queensland's second largest load is located 900 kilometres to the north of Townsville. The power stability at Gladstone is far better than that at Townsville, and the transmission costs much lower. On the other hand, power stability is an issue at Townsville at times. A feasibility study is being prompted by the local Member of Parliament and the Townsville Enterprise Group to identify if a large-scale power station is viable in the region. The ramifications could be to undermine the viability of other stations. Good morning, I'm Alex Thorogood from EcoDrive. Welcome and thank you for taking the time to consider my research into SINES, Switched Intelligent Grid Network Systems, an alternative approach to power quality. Looking at the graph, energy demand against cost, it can be seen that between 1400 hours and 1900 hours, the price of energy spiked to over $140 a megawatt hour, whilst from 2000 hours that day through to 1300 hours the next day, the energy cost per megawatt hour remained below $58. To encourage users to use energy at off-peak times, retailers offer an off-peak rate, providing the energy load can be switched off. At peak times, the energy loss over the distribution network is at its highest, causing voltage sags and distortion. Surprisingly, 10% of all expenditure on the grid supply in Queensland caters for less than 1% of the load. Whilst the actual cost of energy by consumers is currently averaged across the day, it is clear that those consumers that use energy at times of low load and little at peak load are offsetting the costs to consumers who use large quantities of energy at peak times. The advanced metering currently being rolled out across Australia has the potential to dramatically change this with real-time metering. The new metering, expected to be fully operational across Australia by 2017, will have the capacity to offer and charge variable rates depending upon time of use. The main difference in transmitting energy over long distances as opposed to short distances is the added impedance, causing volt drop and dual loss, as well as line loss due to corona discharge and tracking. If we consider a diving board analysis, where the board represents the length of transmission and distribution network, it is easy to see that closer to the load to the support or power station, the less influence of changing loads. As the load moves away from the power source, the stiffness is lost and greater deviation creeps in. To limit the power loss, transmission voltage is stepped up, such as at Gladstone, where the main feeder heading south is at 250,000 volts. Stepping the voltage up lowers line current and hence resistive power loss, but it does increase tracking and corona discharge, as is currently being experienced between Perth and Kalbarri. The starting of heavy loads connected to long transmission distribution networks may cause voltage sags and currents. There are a number of compensator arrangements installed at different locations, controlled to supplement the power quality conditions such as voltage sag, power factor, as well as overvoltage. Pictured as a swirl line transformer at Point Lowly in South Australia. The transformer has a feed-in voltage of 19 kilovolts and supplies a number of domestic dwellings at 230 volts. Note the discharge and tracking associated with the environmental conditions. Adding transformers also adds loss, with transformers being less than 100% efficient, but I may also add flexibility with auto-tapping, changing, enabling some compensation for changing loads. Power quality issues include reliability of supply, voltage limitations and variations, power factor, harmonic distortion and frequency stability. Power quality issues are further being challenged by embedded generation such as grid-commutated PV systems. The aim of the initial generous feed-in tariff for grid-connected PV systems was to encourage investment in renewable energy and to aid in Australia reaching the mandatory renewable energy target. South Australia, Queensland and Western Australia have seen the greatest uptake of PV grid-connected systems. In 2011, an article appeared in the Courier Mail flagging that the grid system transformers in the Sunshine Coast region had reached saturation and there was no further capacity to cater for additional grid-connected systems. Grid-commutated PV systems to push energy onto the grid cause a slight rise in voltage. Where the impedance connecting the system to the grid is high, the voltage rise will be greater. The voltage waveform in the slide is taken from an installation where on a regular basis inverter disconnects due to high voltage. Note the change in voltage when the array is in full sun. The effect is becoming more prevalent in many areas, particularly where there has been a vast uptake of PV grid systems. Consider the load versus PV input graph taken at the same location. Note the peak loading does not occur at the time of maximum PV output, meaning that a substantial quantity of energy is being transported to the grid. Limits of PV penetration is currently being studied by an international energy agency involving 13 countries, and a seminar titled Task 14 being held at University of New South Wales in November of 2013. The aim of the seminar is to navigate a way into the future with greater PV input and overcoming limitations. Some of the findings and future areas of research from that seminar were: the installation utilising PV will become economically focused on self-consumption, battery backup be explored to improve reliability and to better utilise PV input, the battery-backed grid inverters be considered to act as compensators on a demand response basis to tackle power quality issues and to improve the level of renewable energy on the grid, smart grid technology, remove the technical barriers that inhibit high penetration of PV onto the grid. The energy profile shown in the slide is of two different domestic installations on the Sunshine Coast of Queensland. Home A has a grid PV system sized at 1.5 kilowatts and Home 2 has a 3 kilowatt PV system. At the time the arrays are generating maximum energy, the installations are consuming their least. For self-consumption to happen for each installation, either the array needs to be downgraded or the energy generated from the array is stored and used at a different time, most effectively at peak times. From this research, experimentation objectives established are to gain a level of autonomy from the grid, to improve power quality by using a storage buffer system, to enable grid-connected array to act as a demand response device for self-consumption of energy generated, increase renewable energy into the energy use profile. Stage 1 of development, the buffer model. The voltage waveform in the slide is taken from an installation where on a regular basis inverter disconnects due to high voltage. Note the change in voltage when the array is in full sun. The effect is becoming more prevalent in many areas, particularly where there has been a vast uptake of PV grid systems. The second stage of development was to couple a grid-connected inverter on the grid side, with the challenge being to control the PV to satisfy load without actually feeding onto the grid. This was achieved by controlling the array feeding to the inverter and monitoring load current, switching strings of the array in and out as needed. The inverter used in this part of the experimentation, chosen because of its low window voltage, 50 to 100 volts, was Electronics PV Edge, built in Caloundra, Queensland. The array was manually configured numerous times before a series of solid-state relays were added and multiplexer decoder circuit installed. The aim of the experiment was twofold. One, to prove that the grid-connected system could be used as a DRED, as well as being able to be controlled by the load, aiding installation to consume the energy produced. The picture in the slide shows the system on the AC side switching from no load to full load, being controlled by the Science 1 model. The slide shows the energy consumption taken in 30-minute intervals at Triple N Holdings on the Gold Coast, taken over 2 days. It should be pointed out at this stage that the graph shows the accumulated energy use and not the actual real-time load. The profile includes a number of thermostatically controlled heating boosts, which are purely resistive, as well as a 29 horsepower compressor star-builder connected, starting at odd times. Day 1, which ends at reading 48, shows that there is room to fit a large array and absorb all of the energy generated. Day 2, from reading 49 onwards, shows that if a large array were connected, it may feed generous quantities of energy back onto the grid. If the model demonstrated in stage 2 of the experimentation could be adapted to switch multiple grid-connected systems in and out depending on load, then a proportion of the energy consumption at this installation could be supplied by renewable components without feeding onto the grid. The finding at this stage in this model is that further research is warranted. Stage 3 of the experimentation is to modify the buffer model to include PV system on the DC connected side. The most inhibiting factor at present for standalone power systems currently is the cost of storage batteries. In this model we keep the battery storage to a minimum, designed primarily to cover the peak loading times to reduce the loading on the grid. The findings were, as with the buffer system, there remain major disadvantages. Firstly, the limitations on the load capacity, and secondly, the cost of payback time. The major problem with large PV systems, as shown in the slide, is that the energy being generated by the array occurs when typically loading is low. In a standalone system, the energy collected at this time is stored in large batteries. The final stage of modelling is aimed at creating a virtual standalone system with batteries sized to achieve only 4 hours autonomy, once again offsetting peak time. In this model we set out to achieve and overcome the limitations of the buffered models highlighted in models 1 and 3, whilst achieving a close as possible to standalone without the expense of large batteries. In this stage of the array is sized to charge the batteries at their maximum rate with the aim of enabling the array to soak up some of the installation's daily loading, as well as moving some of the energy to be used when the array is not operative as shown in the slide. The second stage of development was to couple a grid-connected inverter on the grid side, with the challenge being to control the PV to satisfy load without actually feeding onto the grid. This was achieved by controlling the array feeding to the inverter and monitoring load current, switching strings of the array in and out as needed. The inverter used in this part of the experimentation, chosen because of its low window voltage, 50 to 100 volts, was Electronics PV Edge, built in Caloundra, Queensland. The array was manually configured numerous times before a series of pictured in the slide is the Electronics changeover switch and the science system operating as standalone, relying entirely on the PV array for battery charging. The second part of the slide is the standalone system working in partnership with Model 2, where the array is being used to prop up the system on the AC side operating a battery charger. The picture in the slide shows the system on the AC side switching from no load to full load, being controlled by the Science 1 model. A closer look at the surge loads shows that it occurred on the first day at 7:39 AM when the electric kettle and toaster were operated. The system switched to the grid for 10 minutes until the battery voltage reached 27 volts, and then re-engaged the standalone system. The final slide shows a comparison in crash flows between the grid-connected system and Excalibur, with Excalibur having a payback period in the region of 6 years compared to 10 years for the grid-connected system, and far better cash flows. Whilst the outcomes of the experimentation looks promising, the clear conclusion is that further research is warranted and longer periods of experimentation required for accurate definitive analysis. The components used in the experimentation were not chosen for any particular design, with the rationale being cost and average performance. For this reason, the financial evaluation is suggestive rather than definitive. Excalibur demonstrates that there is possibility to retrofit PV systems with an interface device to control the quality of energy being fed onto the grid. This concept may be explored further to enable grid-connected inverters to act as a partial compensator. Thank you for taking the time to listen to the results of my research, and please feel free to send questions to Alex at www.ecodrive@y7mail. Thank you.